So yeah, I'm going to talk about SMT proofs and how we can leverage them to make cool stuff. So I'll talk about I like to give an introduction why SMT solvers matter, but also why we should be able to trust them more than we actually can in general. And yeah, that's a good point. It stands for satisfiability modulo theories. So one of the things I'm going to do in a few slides is to define better the problem and give a few examples. But yeah, let me write satisfiability modulo theories. So it's the lifting to first order logic of the satisfiability problem, the Boolean satisfiability problem. But I'll give more details soon. So yeah, right. And then I'm going to tell a bit about integration with proof assistance, which is what we should care about more in this venue, and what are the things that we are doing that we want to do afterwards. Also, I want to emphasize this is joint work with a lot of people, because it's a lot of work to produce proof from SMT solvers and also a lot of work to do this kind of integrations with other systems. So a big shout out to all of them. I'm not going to say the names, otherwise I'll stay here a while. So I love this picture, start every talk with this picture. Formal method applications, they use SMT solvers a lot. And why? Because SMT solvers provide push-boot automation. So you have a very expressive language, first-order logic with theories. These theories in this case are things like arithmetic, data structures, and so on. So it's very useful to formalize things. And you can automatically solve problems in a very scalable manner. So people care about SMT solvers a lot in these domains. So a good example of something that has happened in the last years that has really driven more interest in SMT solvers is the extensive use by AWS, Amazon Web Services, of SMT solvers to do verification in several critical things. And as these things are used in critical settings, then you start to worry about, I'm trusting the solver to say, for example, that something is secure, but what if the solver is wrong? Then it means that what I'm saying that it's secure is not very secure. Okay, so this is bad. So we should be able to trust the solvers. But here we are concerned with something else, like proof assistance, right? So how proof assistance may use SMT solvers is something we're going to talk about more in details afterwards. But the idea is that SMT solvers could solve, similarly as to these other applications, the problems that arise when you're using proof assistance, right? So you write a theorem, you are in the middle of writing the proof, and then could the SMT solver solve that part of the proof for you? And in that case, you are going to trust the system that it did the proof correctly. But if the system was wrong, then it's catastrophic, right? Because your proof now that you think is right is wrong. And we cannot have that. So that's the context here, okay? So why can't we trust SMT solvers? Because they're big. They're big because they have to be very efficient. They have to do. Sorry.
I've got a question about this catastrophe. The proof assistant like Isabelle or Sledgehammer is reconstructing a proof, right? It's not trusting the SMT solver at all.
Yeah, I was in doubt about writing catastrophic or useless because.
Useless, I don't understand totally.
Yeah, no, that's the thing. So but for what I wanted to say, catastrophic was better because if you do not trust the solver and you are skeptical, which is what you should do, which is what I'm going to say now, then it's useless because you're just going to discard it. But if you were to trust it, then it's catastrophic. That's what I wanted to say. So. Right, so why is it hard to trust them? At face value, you should not. As an SMT solver developer, I tell you, don't trust solvers in general. Because they're big, because they have to be very efficient. These are languages where it's easy to get stuff wrong. And mind you, the systems are very robust, it's hard to find bugs, but they can be found, and we cannot provide formal guarantees that you're not going to have a wrong answer to your very particular problem in general, right? So as we try to do many things, still it's soundness bugs happen, people doing fuzzing find them. SMT comp is a competition between different SMT solvers, and inconsistencies are found between them. You had a question?
Yeah, so if I find a bug, how quickly will it get fixed?
Many things go into that. So first, how hard it is, then how much human effort is available to deal with your bug, and that varies between who you are. So it's hard to say.
If it's a soundness bug, it'll get fixed fast.
Okay.
So yeah, soundness bugs, which are the kinds of bugs that we would be concerned here, we care about a lot. Like if you found one, please tell us. We'll try to fix it as quickly as possible. Yeah, I should have emphasized that. Like, we don't want our system to be unsound. Like,
Can I
okay.
just ask how many people work on CVC5 and stuff? Like, what's roughly the number of developers?
So here there are like 13, I think, but these are not everybody. Like in these are the people that have worked in the proof production capabilities. The CVC5 solver, we published the paper because it changed it from 4 to 5 recently. The paper had 17 authors, I think. Yeah, it's a lot of people. Like it's a team distributed across 4 universities now in 3 continents. I mean, the continent that's not North America has only 1 people in Brazil, 1 people in Israel, but you get the idea. So like, it's a lot of people, like, because to have a state-of-the-art industrial strength SMT solver, it's a lot of work. So like, oops, I'm going back. No. Yeah. So one thing that you could think is, why can't I just prove the code is correct? The solver is going to be always correct. We would call this certifying the solver. Well, first, this is very, very costly to do because you have a very large code base. You are writing code in C++. When people do this, you generally pay a price in the sense that since it's so complex, you want to simplify it so you don't formalize everything, so you kind of cripple the system a little bit. And moreover, once you do this, I mean, you have spent so much effort in having the system correct by construction that you don't want to change it, right? So you freeze it. So this is a valid approach, like in several settings, but for what we are doing with a system that's evolving daily, like we cannot go this route. So we use proofs. What the idea is to produce a certificate of what the solver has done to solve the problem, and that can be checked independently. So we decouple confidence from the system that we have implemented, and this can be established by third parties. So just to give you a sense, like these are 2 different proof formats that we support, and the proof checkers, these are ad hoc proof checkers in the sense that these are programs that people wrote to check proofs in these things. They have not proven these systems are correct themselves, the checkers. There are other approaches for that, which I'm going to mention afterwards. But you can see like an order of magnitude here difference in terms of the size of these things, right? So it's much, much simpler to check that the solution is correct than to actually find it. And we can, of course, go the route of using proof assistance, which is what we want to do here. Here, this setting, not in general. In which you can import, for example, the proof that the solver did into the logic of the proof assistant. And this, since the proof assistant has an internal verification module, as we have seen before, then it can tell you that according to my correctness, this thing is correct. So you should be able to trust it. Okay?
I've got a
Yeah.
naive question. Can you give a simple example of a mathematical statement that would be proved by such a system?
Yeah. No, not this one. This one. This is an example. It's not very interesting, but it has a reason of being like this, which is it combines different theories. I'm going to get to it in more detail very soon. But satisfiability modulo theories is first-order logic. So whatever you can write in first-order logic is something that can be accepted by such a system.
And by theories, does that mean the same thing as like a model theorist might call a theory?
Yeah. Correct me if I'm wrong, people who... Okay. yeah. So you have the standard model of arithmetic and things like this. So it's not axiomatic and so on. So it's what you would expect. Right. Oops.
Sorry, excuse me?
Yeah.
Are you going to tell us what an SMT solver is? Or because I have no idea.
So as an SMT solver is something that solves the SMT problem. I'm going to define the SMT.
Okay, so you're going to tell us.
It's a circular definition.
I thought I had to do the whole definition. So I'm going to define the problem, then I'm going to show in detail what goes into this thing, and this is going to correlate directly with the challenges of producing proofs from it. It's going to, yeah, I realized that I should have organized differently for this audience, these slides, I think. Okay, so once you have proofs, I mean, there are many things you can do. What we care more about is the correctness thing here, and of course, the integration that you can do with other systems. But given that a proof is a concretization of the logical reasoning the solver has done to solve that first-order logic problem, then there are many things that you can do other than just assert that it's correct or communicate. You can use for debugging, because you can see how the system was reasoning. You can, like, as you are formalizing also what the solver has done, you're going to understand the code better. You can try to do analysis on the data that's generated by saying how the solver is working and so on. But our concern here is these two things. So SMT solving, the way that these systems are implemented, they are a combination of propositional reasoning and theory reasoning. And theory reasoning is how you would reason about these different theories here, as we have established what theories would be. So if you have arithmetic parts of your problem, you would reason with a solver for arithmetic. If it's linear, you would use simplex. If it's nonlinear, you would use things like cylindric algebraic decomposition. To do equational reasoning, you'd use congruence closure. It's an algorithm for reasoning about that. If you have combination of theories, there is a framework that you use for that, and so on. So an SMT solver is a combination of all of these components to solve a problem that you split in several parts. But let's go to the definitions of what these things are. So first, Boolean satisfiability. This is the problem of asserting whether a formula in propositional logic is satisfiable. So can I make the formula true? I'm going to define here a formula directly in conjunctive normal form, because without lots of generality, you can always go into this form. And what we want is to find a valuation for the variables that makes the whole formula true, a model, right? Is this formula... Sorry? Vertical line. Or, yeah, this is in BNF as I'm writing the grammar. So a formula is either a C, which is a clause, or a conjunction of formulas. And a clause is a variable or a negation of a variable or a disjunction of clauses.
And those two clauses don't have to be equal, even though it says C or C.
Right. Right.
Oh, so it's not a circular definition.
Right.
Think of it as an inductive definition.
Yeah.
Right. Invisible math, right? So. yeah. So, yeah, I am not a math person, right? So I think it's very clear. Is this formula satisfiable? So can I find a valuation for this variable such that this formula is true, where this symbol is conjunction, this symbol is disjunction, this symbol is negation? Yes, it is. There is a model, which is this one. If you substitute the value of these variables per this one, then it's going to be true. And it's very easy to check, right? You just have to substitute and evaluate. Is this one satisfiable? There are many ways in which you can reach this conclusion. One of them is probably not, because what would be the point? It's not, right? Why? That's the thing. Why? There is no combination of valuations for these variables that would make this formula true. There is a simple way to see this, which is to enumerate all the possible valuations. There are only 8 here. If I had 1,000 variables, it would be harder. So I would have to construct an argument for why this formula is unsatisfiable. That would be a proof. So this is what you are going to be interested at. For this thing here, which is propositionally unsatisfiable, I can have a proof that uses resolution, propositional resolution. The resolution rule is that if you have this and this, it's valid to infer this, okay? That's the resolution rule. So with this rule, you can build proofs for propositional logic. This rule is enough. You can do everything with it. So you can then construct an argument that your formula is unsatisfiable because I can have this proof. And then you can have a tool that understands what resolution is, and then that tool can check that your argument is valid by checking the proof. That is the overall idea. Okay, in SMT, things start to get a little bit more complicated. First, the language is different. So I am defining here now how I can write formulas in first-order logic. So first I have terms. A term is either a variable or an application of a function over terms, where this t here is a variable that can be instantiated with this guy or this guy, right? Again, an inductive definition. And a formula is a predicate applied over terms, or the negation of a formula, disjunction, or a quantified formula, where I have a quantifier here with a list of bound variables that can occur bound in this formula. So this is a way of representing formulas in first-order logic. And then the satisfiability problem for SMT, satisfiability modulo theories, is that given a set of theories, and what are these theories, then you can think of them as models that you have to extend to build a new model for the whole formula. Then if you can build such a model, then the formula would be satisfiable. So this is an example where we would test satisfiability, where I have integer arithmetic. So these variables here, x1 and x2, they range over the integers. The symbols like this one and this one are what we expect in integer arithmetic. This is equality, as defined such that non-syntactic equal things can be entailed equal for different reasons, like congruence. If x is equal to y, then f of x must be equal to f of y, for example. F is an arbitrary function. This is what we call an uninterpreted function because it has no fixed interpretation. Okay? That's an SMT problem, for example. And this problem involves two theories. It involves the theory of equality and the theory of integer arithmetic. And the way that we can try to solve this problem, for example, is reasoning about three things separately. One is the Boolean structure of the formula. The other is the equational reasoning. And the other is the arithmetic reasoning. Okay? So propositionally, we know that since this is a conjunction, for this formula to be true, this, what we call a literal, must be true, as this one must. And since this is a disjunction, only one of them needs to be true, right? Okay.
Sorry, how are your parentheses working here?
Not as great as one would expect. So
The mouse, because it's kind of
this
hiding.
thing here should be under parentheses, and this one should also.
But of course the question is, which one comes first, conjunction or disjunction?
No, the brackets around the or.
Yeah,
Oh,
so,
sorry. Oh, yeah.
There are
There is a little
parentheses
hand
around
there
the
that's
disjunction.
Yeah, move the hand. It's blocking the.
sorry.
Yeah, there you go.
Oh, okay.
It's not blocking anything.
Yeah, I don't understand how. Okay, but but yeah, okay. So we are on the same page, right? So the point is, these two must hold, and only one of these needs to hold. Okay. So what can then we infer based on the theories here that can help us solve this problem? So yeah, this is a separation between theories of these different literals, which means that as an SMT solver works, these literals go to different theories, solvers within the solver, so they do things separately and then they communicate with each other. We know from linear integer arithmetic reasoning that from these two literals I can infer this one, right? This is valid in integer arithmetic. The only possible value for x1 is 0. However,
Is that supposed to be an equal sign?
Yes.
yeah, but as we have discussed, equal is complicated, right? So like,
It's just to say that's a syntactic equals, not a semantic equals. That's why we use a different
No,
symbol.
No,
that's
it's
a
the other way
semantic
around.
equal.
This is the semantic one, not the
Yeah.
syntactic
No,
one.
that's a formula you're writing, right? x1 equal to 0 is a formula. It's a syntactic object.
Yeah, okay, yeah. It's because I think one can go either direction depending on where you're starting from, but so logically they can be equal, they don't need necessarily to be syntactically equal. That is the idea. So, I mean, x1 is not the same as 0, however, if these two things hold, necessarily a value for x1 needs to be 0. That's what this equality is supposed to say. All right. So another thing that we can infer now via EUF is equality in uninterpreted functions, as we call it as a theory. So it's the part of the solver that reasons about equality and the functions that are free, that have like free possible interpretations. I can apply congruence here that given that x1 is equal to 0, necessarily f of x1 must be equal to f of 0. Therefore, this guy cannot be true, right? Necessarily, then this one needs to be true. However, I can infer that since x1 must be equal to 0, x2 plus x1 cannot be greater than x2 plus 1. So this problem is unsatisfiable. Okay? So this is what an SMT solver does at a high level. It takes a problem that is written ranging over different theories. It breaks it apart. It reasons separately propositionally and theory-wise. Propositionally, the reasoning is done by a SAT solver, which is solving the Boolean satisfiability problem over the abstraction of this problem as a Boolean satisfiability one. And the theory solvers are dealing with each theory separately and communicating between each other, such that when the linear arithmetic solver infers this, it tells the EUF solver, and then it says this, and so on.
Okay.
Yeah.
And the theories have any relation symbols or function symbols in common?
Yes, but things start to get very complicated. So you should ask these two guys here, that like they're experts in theory combination, because things get very complicated when that can happen.
Generally, we only share equality.
Mm-hmm.
If you share more than equality, it gets messy.
Okay.
Would you expect these theories to these I don't know the term for it, these solvers to be complete in any way?
That varies per theory. So for example, here in this example, we have no quantifiers. Generally, when the problems have no quantifiers, the theories solvers are decidable, but that varies. If you have strings, for example, with length and concatenation, decidability is open. Then if you have quantifier-free nonlinear integer arithmetic, that is also undecidable. So we have a combination of decidable and undecidable solvers. So there is a lot of heuristics going on because you cannot have the expectation that these things will terminate, right, when you give it to it a given problem. Yes?
So there's tacitly, so is it a there exists an F such that, is that kind of tacit?
Say that again, sorry?
So I'm just a bit, so I'm happy with, when I look at that formula, I'm like, okay, there exists an x1, there exists an x0 such that blah, and is there also kind of tacitly and there exists an F?
Yes.
That's what satisfiable means. So satisfiable means everything is existentially quantified. Yeah.
Yeah, so it's as if you had existential quantifiers and you scolemize them before you start solving. Okay? Yes?
So, are there any satisfiable modular theories where, like, you can say, does this point belong to a variety in the real line? Like, does there exist a point x comma y that's on the circle x squared plus y squared equals 1? Or are those much more difficult?
How's this theory of real closed fields?
Yeah, so we have a theory of real closed fields. Like,
Well, we support, yeah, real close.
Yeah, yeah.
Nonlinear real arithmetic.
Yeah, exactly.
Yeah.
Thank you.
And obviously there's not one for the zeta function, right?
You lost me there.
We have to define zeta function.
Moving on. So this is how we would write a proof for the unsatisfiability of that problem. Here now we have more than resolution, right? So as I said, we have the combination of these three things for that problem. We have the equality reasoning, we have the resolution reasoning for the propositional part, and we have the arithmetic reasoning that I called Pi1, such that things would fit. So this is a way that I could construct a proof of the unsatisfiability of that problem, right? As we discussed it. And in principle, this is what the SMT solver is doing. As we'll see afterward, this is not how CVC5, for example, solves this problem, but it could have done it like that. All right, so then what is difficult about producing proofs? The difficulty is, I have tried to hint, an SMT solver has a lot that goes into it because you have all these different components communicating, so it's very difficult to collect and store information efficiently to keep track of everything that you have done during solving. Moreover, there are things that are very hard to just preprocessing and rewriting, is like simplifying the problem before you actually solves it. So there is a lot that goes into this. It's hard. There are things that are incredibly hard to model proofs for. We have no standard proof format because it's very difficult for many reasons. And have scalable trust for checking can also be challenging for reasons that I will not get into much here. All right, so as a motivation slide, so we wanted to address these issues, and we started years ago, like to have a journey to produce proofs for CVC5, which is the successor of CVC4, it's a state-of-the-art SMT solver, where we would address those challenges, or as many of them as we could.
What does CVC stand for?
Cooperating Validity Checker? Yes. Started with Clark Barrett many years ago. Yes, so we changed the way of writing from 4 to 5. It's no longer capital letters. Just we're trying to spread the word. Yeah, it's hard to do these changes, right?
Lowercase letters are now allowed?
It's more modern, I guess. I don't know. I like it better. I don't know how we come up with that decision. Anyway, so yeah, so we started from scratch, right? And then there is a lot that goes into this, and then we wanted to make our life easier. So we wanted to have a modular infrastructure. This gets a bit technical, maybe not as interesting. And when we had the capabilities, it's quite cool, of producing proofs both eager and lazily. The idea is that if you want to keep track of all the details of the proof as you're solving, it's hard, but you can just say, I'm going to figure this out later. I'm going to have an elaboration algorithm that's going to fill in the details afterwards. This would be lazy proof generation. As I mentioned, there is no standard proof format for several reasons, so we said, okay. And then we have different proof outputs that they are used according to who is using our proofs. And then I'm going to highlight the Lean one, because Lean is very much discussed here. Yeah. So this is an SMT solver, right? SMT solver receives a formula, and then it tells you it's sat, it gives you a model, or it says, well, when it terminates, it can happen that it does not. Or it can just give up and say unknown. It can also happen, but let's pretend it always reached this stage. And then it can say false, which is unsatisfiable. So the negation of your original formula is valid. It's a theorem. We care about this case, because it's when we get a proof, right? So we want this. We want this object that has this type. So don't care much about notation. This is very informal. It's just that from this formula, we can infer false. This is what this represents. How I build that? That is the question that we had to address. So again, an SMT solver has several components. One of them that is crucial for performance is the preprocessor. It tries to simplify the problem as much as possible before you start solving, because solving, you're searching, and it's hard. This is doing things that don't involve much searching, so it generally makes the problem much easier. One thing that it does that's quite important is what we call, well, there's no standard name, but we transform some equalities into substitutions, and then we remove symbols from the problem. This can make it much, much simpler. And it's hard to track this because you're reasoning globally about your formula. So this is something that happens here, for example. So we are transforming this formula into a set of new formulas, and we need proofs for them.
Can I ask a quick question?
Yeah.
The t prime in the bottom line is supposed to be a variable, not a term. Is that correct? Like a fresh variable or something?
Yes. Yes. So we use Joyce for introducing new symbols, the Hilbert's epsilon operator. So classical reasoning, right? Like as in non-constructive. That's where we are at. Okay, so for the preprocessor, then we need a way to guarantee that I have an explanation for the derivation of each one of these new guys from the original formula. That is the first thing. So we have what we call this post-processor, which is going to be things that tie up the proof afterwards, because we have all these modules producing different parts, and then we combine everything in the end. If we open the box, then we have the combination of these two things. We have a SAT solver that is reasoning about the propositional structure of the formula, and we have the set of theory solvers that are considering the different parts according to the different theories that they involve and how I reason about them. A SAT solver works on formulas in conjunctive normal form, so we have a clausifier that reduces the formulas into clauses. And I need a proof of this transformation that I also am going to store here in this post-processor just for the propositional part. So what the propositional thing says is I have all these literals in my formula. Some of them must be true such that the whole formula is true. And the question then becomes, propositionally speaking, the question then becomes, are the theories okay with all these things being true simultaneously? They may not. So what happens in the theory engine is that each one of the theories, they reason a bit about their specific literals, and you combine the reason that they establish in the end. So for example, so we had that example that x1 had to be bigger or equal than 0, is smaller than 0.
Smaller than 1.
Smaller than 1.
Otherwise, it's inconsistent.
Yeah.
Oh, yeah. Thank you. So I had these three literals asserted by the SAT solver that they must hold. And then the theories are going to say, no, they cannot hold simultaneously. So then a lemma is going to be generated. This is a disjunction, where either this guy is false, or this, or this. So this is what an SMT solver does. It generates a lemma, which is a valid clause, a valid disjunction, according to the theories of integer arithmetic and equality. So this is sent back to the SAT solver. And now the SAT solver has to find a new set of literals that simultaneously are true and make the formula true. In that example, it would have had to make x2 plus x1 bigger than x2 plus 1. Thank you. Yeah. So what it was going to do then, it was going to try to make this, and this true simultaneously, right? Which was also not going to be possible. So we're going to generate another lemma, and this other lemma would make it impossible for the SAT solver to find a set of literals that were true such that the whole formula was true. Therefore, the formula is unsatisfiable. That's what an SMT solver does and how it solves a problem. So you have this interplay. Eventually, the theory engine will field all the possibilities that the SAT solver had to make the formula propositionally true. The formula is going to be false in the case the formula is unsat, right? And then you're going to have a proof from the SAT solver that from these clauses you can derive false. Okay. So now the solver has finished doing its thing, and we must combine the different components into a full proof. So we must combine the proof from the clauses into false, from the clauses being derived from whatever I had been classified, be it preprocessed formula or lemma. So this is done by this post-processor. So I have then a proof that from the preprocessed formulas I can derive false. Since the theories are producing just valid lemmas, I don't have dependencies from them. And now I must combine the proof from this guy into false from the original formula into the preprocessed one. And this is what this other post-processor here does, and I'm done. That's what happens. All right, so several things went into this. So this is the overall architecture, right? There are many different important components. One of them is what we call the internal proof calculus, which is just a representation of every possible step that the solver can take. So we must have inference rules that account for them. And of course, since you have many different kinds of reasoning that are applied for different theories, basically each theory has its own proof calculus, right? So this gets big. So we have a specification of the rules of the calculus from CBC5 in the website. There's documentation if one wants to check it. I check it a lot when I'm doing the conversion into Lean to remember the semantics of our rules. And one thing that is crucial to make this production of proofs is what we call the proof generators. So one thing that is very important, that I had mentioned briefly, is the idea that you are not always generating the proofs as you are solving. So you are often generating a promise of a proof, if you know JavaScript, that when you ask for that proof, then only then it's going to be given to you. And we only ask for proofs in the post-processor. That's the idea. And these proof generators, each one of them has its own way of generating proofs, basically, that is dependent on the part of the solver it's producing proofs for. So yeah, that's what I just said. So to give an example, one thing that's very important is for substitution and rewriting. That we do have a rule that is very expressive, which combines both substitution and rewriting. So as we are solving the problem, we just use this rule. So you'll see that this equality holds because if I substitute A and B by these values, then this becomes equal to false due to arithmetic and propositional reasoning. So all of that is combined into this single rule. And only when I get to the end that I ask for a proof, I can expand that. So for example, this thing expands to this one, where I split the reasoning between the part of the substitution and the part of the rewriting. And moreover, the rewriting can be further split into rewriting due to arithmetic and rewriting due to Boolean reasoning. So this happens lazily, as we say, because only in the end of the solving do we ask for the proof of this step. I may have generated several of these steps during solving that I don't care about. I only care about the one that was part of the things I needed to derive false. And only those get expanded. So we have a proof generator that specifically deals with this kind of proofs. For other kinds of proofs, we have other proof generators. Okay?
Sorry, can you explain that again? How is it lazy? Like, in the sense of, like, what do you store at the end that can allow you to expand to the full extent?
So if I understood, the reason it's lazily, that we call it lazily, is because if it were eager, we would have generated this from the beginning. As we derived this fact, its justification is this whole proof. And eagerly, we would have produced the full proof at the moment that we derived the fact. The idea that we do it lazily is that we only ask when we need it. And one thing that is kind of crucial is when you are solving a problem, you are deriving several facts that you may not need in the end of the day to show that the formula is unsatisfiable. So some facts are irrelevant. So if I were to do a complicated proof, so to speak, for every one of these steps, I may waste work because I may not need those steps in the final proof. So I do it lazily in the sense that I only pay for producing the more complicated proof when I need the proof for that fact, which is when that fact shows up in the final proof.
I guess, like, what is the artifact you produce at the end that allow you to reproduce a proof? Like, do you just store the last step of the reasoning, like the last rule you used, or?
So there are different flavors. For this particular case, we store this inference here. So we have these premises, this conclusion, and this ID. We also have some extra arguments, which I don't quite remember at the moment. The kind of substitution, the kind of rewriting that we do, I think. And these information are sufficient for us to reconstruct this proof in the end of the day. So we elaborate this coarser-grained proof into this finer-grained one. For this case, it is. There are some cases where there is some search involved, but for this case, it's direct.
By case, you mean this example or some subclass?
For this flavor of proof.
Okay.
Okay? All right. Demo. So, I have this problem here, okay? It's an SMT problem, and this is in nice notation, and this is how we write in SMT-lib. SMT-lib is the standard input language of SMT solvers. It's something that made SMT solvers much more easy to use because they all agree what is the input. It's a great thing. And it uses S expressions, which people don't like. But if you use them enough, you'll learn to love them. So yeah, I have this problem, and you see that? Okay. So this is what we call a proof visualizer. It can visualize CVC5 proofs. So I have written here that proof in SMT-lib. This website is running a WebAssembly version of CVC5, and I can ask for it to generate a... No, that's not fair.
Can you zoom in a little bit? Is that possible?
Oh, no. Yeah. Yeah, so this is... So I have to declare the symbols that I'm using, and then I assert the things that have to be true simultaneously. But hold on, like, this is not supposed to happen. Yeah, that's very unfair, you know, like, I tried this several times, and... No, but this is not it, hold on.
It's not it?
It's not, well, it could be it. This is, you see false here? This is not very big, right? Like, here, false. We are deriving false from a set of assumptions, which are these blue things here. These assumptions are what we have given as input to the SMT solver. And this is folded because it's hiding 28 steps that the solver has done. And this is in brown because the solver solves this problem purely by rewriting, as we call it. So this is all done in the pre-processing phase. You remember it was brown. Maybe the colors will not match after this, but for the pre-processing it does. So all of these steps here show how, via doing simplification on the original problem, I can derive false. What I wanted to show was slightly different, because I wanted to disable the pre-processing that is used to solve this particular problem. Yes. And now I have a different proof, because it solved it differently. So purple means propositional reasoning. So this is what the SAT solver is doing. So it's given stuff. Yeah, I'm not going to go into detail, no? But the yellow part here is clausification, and this thing here, it should have been green, but it's not. It's equality reasoning. So there is congruence happening here, and you will notice that this is the part of the proof that tells that I can infer that f of AC is equal to f of BD due to the fact that A equals B and C equals D. You'll see that there is a spurious step here. This is an artifact of the way that we produce proofs, because we do some things automatically and it's not perfect. But
It's better than doing it 17 times.
I could say that, yeah. Okay. So yeah, this happens. So I like the sentence that John Harrison said yesterday. So to shock you rather than to have you understand anything, this is the proof that CVC5 generates for this strings problem here. Oh man, hold on. So you see, like I have a string variable. It can take any string as a value. I'm telling that its length has to be smaller or equal than 3. But I also am saying that it must contain the IPAM acronym. And this is not possible, right? Yeah, so the way that the CVC5 SMT solver solves this problem is by applying 4,811 inference steps. So it does many things, but it gets there. Strings are hard, really, really hard. Yeah, that's what I wanted to say. So this is a dot representation of our proofs. It's one of the proof formats that we can input proofs on. Yes?
Out of curiosity, if you change that 3 to 5, then it's going to give us a string that satisfies the...
Then the problem would no longer be satisfiable. Then
it will be satisfiable.
Yeah, sorry. It would be satisfiable. This thing would break because it expects the problem to be unsatisfiable, the visualizer. But the SMT solver would tell you that it's sat, and it would give you a model which would be a value for X that satisfied the constraints.
A specific one.
Yeah. It can give you a symbolic one when you have particular circumstances, but it's almost always concrete. What?
I want to see it.
Press run.
You want to see the model?
Yeah.
Oh, hold on. Yeah, it's possible.
Give it a longer string, you can hope that it will say IPAM is cool or something.
Oh yeah, I have it here, okay. See that? Okay. So I use Emacs, as people should, right?
Of course.
Why not
Everyone
VI?
uses email.
At least use evil mode. Yeah?
Let's not get there. So if I run CVC5 on this problem, it's going to say SAT, right? So
And then we cannot see
We don't see it.
We'll see it now. Give it again.
Okay.
Yeah.
it's deterministic for some. And I can give this option, and it's going to print a model, which is a valuation for the variables that makes the formula true. In this case, it gives it works, right? It's good enough.
Because it was less than, yeah.
If I had said it must be equal to 5, then I don't know what's going to happen.
No, we're just...
Yeah, it had an 8.
This will be the name of the next workshop.
So the string solver of CVC5 has 20,000 lines of code. 20,000 lines of code. It's the work of many, many years, thanks mostly to Andrew Reynolds. There is a lot that goes into it, which is why when you get an unsat problem, you have such a proof, right? Because it's hard. It's really hard. Which was a great achievement for us to have full proofs for the string solver, which was what we got due to the architecture that I showed there. So I'm gonna have to talk about Lean. Hold on, Lean, yes. Where are the slides? There you go. So, proof assistance. We have proofs. So we have a logical justification of what the solver has done. And we can use that to have interoperability between proof assistance and SMT solvers. How can we achieve that? So you can solve a few problems. So if you write theorem in Lean and then you encode that theorem as an showing the validity of that theorem as showing that its negation is unsatisfied when SMT. If you have that SMT solver solves the problem and gives you a proof, and if you can convert that proof from the SMT solver into a proof in the language of the proof assistant, then the SMT solver has solved the problem for you. So remember when Leo in his talk said that the grand challenge, the first one, was automation, and that we know how to do automatic reasoning first order logic very well, and that we could maybe lift that to dependent type theory. That's what would get to it, but it's hard. So we are doing parts of it. It's hard, but it can be done, and it has cases of success in other proof assistants, such as Isabelle Hall and SMT Cox, especially in Isabelle Hall with Sledgehammer. There are two approaches to do interoperability, certified versus certifying. It's the same idea of correct by construction versus producing a certificate. We think that certifying is more flexible. That's what we are doing. So we have this work in progress, Lean SMT, which is a tactic that you can invoke from Lean that encodes your problem as an SMT problem. It gets the proof the solver produces, lifts it into an original Lean proof, and then you can discharge automatically the given goal. So in Isabelle Hall, sledgehammer, as people have said, there is a quote by somebody that I don't remember, said in a slide by somebody else, that it's the difference between walking and running. Because, so like it's that idea that when you're using a proof of system, there are things that are obvious to you that you wanted the system to get automatically, it will not. And these are the things of, the kinds of tactics that would very easily get the problem for you if they were to work well. Because you don't even need to think what is the kind of reasoning I'm going to be applying to this step. You just call this hammer, this tool that can solve problems in this very general fragment. And if it can solve the problem and the proof can be reconstructed, then you can move on to more interesting things in your proof.
Just the talk is by Jasmin Blanchette, and the quote is either Tobias Nipkow or Larry Paulson.
Good, thank you. So there you go.
Larry Paulson.
Yeah, I knew that the slide was from Jasmin, but I didn't know who was the author of the sentence. Thank you.
Is there any reason to say why one could expect to convert a Lean proof goal into an SMT problem?
I guess you
Special
don't
cases,
use
you
time.
can.
So there is a gap in expressivity, right? So you have a much more expressive logic independent type theory. So doing the conversion to first order logic, this conversion can be very complicated, and you need to do it in a way that you must be able to go back. So this presents a significant challenge. So just to give a very simple example, is like in this language independent type theory, you have polymorphism, for example. You can quantify over types, and you cannot do that in first order logic. So this is something that you must be able to encode in one way or the other. Yes?
So in Sledgehammer, it's not using a reconstructed, I mean, the proof from the SMT
That
is not used, right? It's just using the lemmas that go into the proof, and then something internal to Isabelle is doing the...
It does many things. So it does this that you just described, but it also does an integration of SMT solvers to reconstruct the proof from the solver and have that as just the justification for the validity of the goal. It uses Z3 and Verity to do that. These are solvers that can produce proofs that Isabelle has internal tactics to reconstruct.
So what's the difference between CDC and the sledgehammer and the SMT cock?
So Sledgehammer and SMT cock, these are tools that run in the proof assistance. And what they do, so they are effectively tactics for solving problems in the proof assistance. And they do the three things I was saying here, in which they encode the problem into SMT, they call an SMT solver on that problem, they take the proof from the solver, and then they import it into the proof assistant. So these tools are doing this. And this Lean SMT tool that we are in the process of developing similarly does this as these other tools, using CVC5 to solve the problem and produce the proof. So to do this tactic, we have to do these other two things, right? To encode the problem into SMT. Abdal and Wojciech, who is somewhere here, like have worked a lot on this. And Tomás Mascarenhas, which is a master student with me, has worked a lot into doing the reconstruction tactics for lifting the proofs from SMT into Lean. Another demo, quickly. Very quickly. Demo. So this example I took from the SMT Cock website. SMT Cock is such a tool as I described for the Cock proof assistant, who uses the Verity solver to produce proofs and lift them. It also uses CVC4. And this is very quickly, like it just, you can write some theorems that show that from the left versions of the group axioms, you can infer the right versions of the group axioms, right? So, for example, you have only the inverse here for the left-hand side. You can also have for the right-hand side. And this is proved from the SMT solver. So this SMT lib problem was generated from the lingo. This was encoded into SMT. And then this is the proof that the SMT solver produced.
Oh my God.
Beautiful, right? And this was automatically reconstruct, well, automatically, it takes 1 minute, unfortunately, to do this. So I did it before. Wow, man. Yeah, this is the final type here. So, and then there are, if you were to look here, I mean, not, hold on, like.
So
Yeah.
these lean S140, and are those the auxiliary lemmas that you mentioned earlier?
Yes, exactly. So all these have here, these are inferences the SMT solver has done in the course of solving the problem. And like, let me find, hold on, like R2. So this is a step that's done via resolution, for example. So the SMT solver is doing resolution, so we have a tactic which is called R2 in Lean that is taking this shape of a proof from the SMT solver and using Lean theorems to validate that something valid. Okay? Yes?
So, I mean, to prove that you have a right identity, then you have to say for all G inside the group, E times G equals G. But maybe I'm just being stupid here, but isn't an SMT solver for existence statements? Like,
No, they can reason about quantifiers as well. So, and which is what is used here. So this involves quantifying instantiations, columnization, things like this. Without handling quantifiers, you can have no hope of being useful for proof assistance because you're going to have many things defined as axioms for your theories and so on. And SMT solvers, they do well enough with quantifiers, like varies, can be good, works. Yes?
It's maybe a silly question, but why are you assuming that G is non-empty if you're giving yourself E is an element of G?
This was the fastest way that I could have this working. I did not put much thought into it.
So it's possible that the SMT solver was somehow didn't know that having an E means that G is non-empty?
No, so I put this more to the benefit of the reconstruction in Lean, figuring out that things were valid automatically.
Oh, I see. Okay. Yeah.
Because the SMT solver by default has that every sort is non-empty. So this is not something...
Yeah, this is the fault of logic textbooks from 1950 or whenever it was.
I think it's wrong.
That was a good idea, yeah.
Oh.
Yeah, lots of stuff breaks down with the empty model. It sucks.
Oh.
So I think it's because you want x equals x to be true.
Well,
It's even more true if there are no x's.
So this x, such an x equals x, is not true.
Why
It's existentially quantified by default, right? So
wouldn't someone prefer the short proof a human would find to that gigantically long proof you showed us?
definitely. But you would have to find it.
Only assuming that anybody is going to ever look at the proof.
they are not easy to find, those two proofs.
Well,
So for instance, in computer science, this might be part of verifying 1 million lines of code, and nobody's going to look at it. They don't care what it looks like.
No, but mathematicians sometimes when they're writing proofs and they have something they think it's trivial, they will not bother to show it. And this is the cases where you would use such a tactic, right?
But you said it takes multiple minutes, right?
That's something that we are working on, you know, like the performance is to be better. But
You just go on holiday.
I mean, you leave a hole and then can you prove this with unlimited time? Maybe it can, right? So
It's still faster than a human. You only think it's easy because you've seen it before. But the first time you saw it took you minutes.
Sure.
Right? I mean, it took me minutes probably.
the minute it took was just to reconstruct. To solve it's less than a second. Anyway, so yeah, we are doing many things. Like, so we are also working with extending sledgehammer with bit vectors. Hannah Lacknett is heading this project. We want to have proofs for nonlinear arithmetic. It's hard. We are doing other things. So that's it. Thank you.